Bismillahirrahmanirrahim. Assalamu alaikum. Hope you are feeling good because I think so. Uh, till now, you have adjusted with the online lectures, and since last week, we have started our lectures on Google Meet, and I expect that your understanding level with the lectures on Google Meet with your question answer session is much better as compared to the first half of this course that was related to symmetry, and I really very sorry for not being able to conduct the classes of first half with you on Google Meet because previously there were no such instructions from the university to conduct and engage the students on Google Meet. Since last week, university has given us directions to conduct our sessions and classes on Google Meet. So that's why since that time I have started to experience my classes on Google Meet, and I am feeling and expecting that your understanding is much better as compared to the previous lectures. This is lecture number 9. That is the continuation of previous lecture. In previous lecture we have studied about magnetic moment of transition metal complexes. In this lecture, we are also going to talk about magnetic moment calculated from the formula and observed from any type of magnetometer, and the comparison of magnetic moments calculated from formula as well as observed from magnetometer. Then we shall have some particular examples, that is nickel complexes and iron complexes, their geometry, their electronic configuration, and we will be able to get a very clear picture about magnetic studies of these complexes in this lecture. And at the end, I have few MCQs for you and some short questions that you will be sending in Google Classroom. For the method of sending assignment, you can write down your answer in any paper, and you can also send image of that piece of paper in Google Classroom. You can also comment or type in Google Classroom. So it's up to you whether you want to write down on a piece of paper and take image and send in Google Classroom, and it's also open choice for you that you can also write in Google Classroom directly by typing. This was the table that we were discussing in our previous lecture, and we studied in our previous lecture that most of the transition metal complexes, their magnetic moment calculated from mu formula, and their experimental found magnetic moment are very close to each other, and we are just taking an overview of the table because this was the table that we left in our previous lecture. And the second half of the table from iron and cobalt and nickel, in this table the second part of the table is representing that there are two possibilities of unpairing of electron. In case of iron plus 3, iron plus 3 can form two type of complexes. One type can contain 5 unpaired electrons and the other can contain one unpaired electron, and this number of unpaired electrons presence is directly depending upon the strength of ligand. Similarly, cobalt can form two type of complexes with 4 unpaired electrons and 0 unpaired electron. Third one is cobalt in D7 configuration has similarly two possibilities of 3 unpaired electrons and 1, and nickel plus 2 can form two type of complexes with 2 and 0 unpaired electron. Although the experimental values of magnetic moments of most of the 3D metal complexes given in the table are almost equal to those calculated on the basis of the number of unpaired electrons in 3D orbital. Yet there are many complexes like potassium hexacyanoferrate and hexaamine, cobalt chloride, similarly hexa potassium, barium, hexanitrocobaltate, and uh, this one complex I forgot the name of this ligand, but anyhow I will find it and tell you what is the name of this complex. BIGH, which do not obey this rule. That is, the actual number of unpaired electrons in the 3D orbital given in the bracket is different from the expected from the valence shell configuration of the central metal ion, and hence experimental value of mu is different from the calculated value of mu. The discrepancy between the experimental and calculated value of mu is due to the fact that number of unpaired electrons in a given complex compound depend on experimental value of mu and not on the valence shell configuration of the central metal cation. Thus, it is experimental value of mu which determines whether actual number of unpaired electrons present in complex compound. This can be illustrated by considering hexafluoroferrate and hexacyanoferrate ions. What is the use of magnetic moment values? What are the applications? The experimental magnetic moment value of a given complex compound can be used to determine the number of unpaired electrons occupying the d orbital of the central metal ion in a given complex compound. The number of unpaired electrons are also used to determine in this way can be used to predict whether a given four coordinated complex compound is square planar, means it has a dsp2 hybridization, or it is carrying tetrahedral geometry, and we know that when there is tetrahedral geometry then the mode of hybridization will be sp3 hybridization. So it means overall the experimental value of magnetic moment is helpful to determine the geometry of any transition metal complex. Whether a given six coordinated complex compound octahedral results from d-sp2 hybridization, inner orbital octahedral complexes, or sp3d2 hybridization, that is outer orbital octahedral complexes. This description, this point belongs to valence shell electron pair repulsion, no sorry, valence bond theory. This point belongs to valence bond theory. In valence bond theory, there are two possibilities that are dependent upon the strength of ligand. If ligand is strong, then it will pair up electrons in d subshell, and there are less number of unpaired electrons, and metal will use its inner orbital for hybridization, and that type of hybridization is known as dsp2. In contrast, when there is a weak field ligand, then ligand will not be able to pair up the electrons, and there will be more number of unpaired electrons, and metal will use outer orbital for hybridization. Consequently, the mode of hybridization will be sp3d2. This point would be clear when we consider the geometries of tetracyanoniclate, tetrachloronickel, hexacyanoferrate, and hexafluoroferrate. Tetrafluoroniclate ion has zero number of unpaired electrons, and definitely it will show diamagnetism, and its geometry is square planar with dsp2 hybridization. In contrast, hexachloronickel ion has two unpaired electrons, then it should be paramagnetic, and its geometry is tetrahedral having sp3 hybridization. The next case of six coordinated complexes, that is hexacyanoferrate, has one unpaired electron, and it should show paramagnetism equal to one electron, and it is inner orbital octahedral in shape, having hybridization T2sp3. But hexafluoroferrate ion has five unpaired electrons, and its paramagnetism, its magnetic moment should be equal to five unpaired electron, and it is outer or orbital octahedral in shape, having sp3d2 hybridization. These are the two different complexes of nickel: hex tetracyanonickelate and tetrachloronickel nickelate. We shall discuss one by one their uh, electronic configuration, their oxidation state, their mode of hybridization, and ultimately number of unpaired electrons present in the complex and their magnetic moment. This is a very clear description of this complex. You can see at right hand side in a vertical direction, there is mentioned nickel 28. Its electronic configuration is 3d8 4s2 4p0. When it goes into plus 2 oxidation state, then the number of electrons present in valence shell will be eliminated, and definitely in this case those 2 electrons will be moved from 4s. So after getting plus 2 oxidation state, nickel still has 8 electrons in its valence shell, and when it's coordinated to 4 different ligands, there are two possibilities. One is mentioned above and little bit a blur image, that is tetracyanonickelate. It's a scale planar geometry. In this geometry, the bond angle between various bonds is 90 degree. And in the later example, tetrachloronickel, the geometry is tetrahedral, and mode of hybridization is sp3, and bond angle in the second example will be 109.5 degree. Here is orbital level diagram for nickel. You can see there are 8 electrons in nickel plus 2. 6 of them are paired and 2 of them are unpaired. dsp2 hybridization means one d orbital from d subshell, 1s, and 2p electron from 4p are involved in hybridization, and the dotted shaded area with empty orbital is showing that d4s and 4p2 orbitals are being involved in hybridization, and after that 4 pair of electrons from cyanide groups will be shared in these empty orbitals, and there will be a formation of uh, coordinate covalent bond between cyanide and nickel. This is the second case. Again, nickel is in plus 2 oxidation state. It has 2 unpaired electron in d orbital. Orbital of nickel plus 2 sp3 hybridization means that 1s and 3p orbital from the last subshell are involved in hybridization, and nickel has 2 unpaired electron in d subshell, and 4 pair of electrons from 4 chloride ions are being donated for the formation of a coordinate covalent bond. In nutshell, tetracyanoniculate has a number of unpaired electron is equal to 0 and it is diamagnetic and its geometry is square planar and mode of hybridization is dsp2, while tetrachloroniclate has two unpaired electron and it is paramagnetic and its geometry is tetrahedral and mode of hybridization is sp3. Now we are going towards next class, that is six coordinated ligands, or we can say which have octahedral geometry. In this case the central metal ion is same, that is iron, but the ligands attached to iron are different. In both of these two examples iron will be written as ferrate because coordination sphere has negative. These are two geometries, square bipyramidal. This is also known as octahedral geometry. In this geometry, the four bonds which are written in a rectangular fashion, these are known as equatorial bonds, and the bonds which are elongated upward and downward, these are known as axial or. So these two bonds upward and downward, these are known as axial bonds. In octahedral geometry, the axial bond angle is 180, equatorial bond angle is 90, and similarly the bond angle between axial and equatorial bond is 90. Here is description of iron atom and cation. Iron 26, it has 6 electrons in D and 2 electrons in S. When it is going into +3 oxidation state, 2 electrons from S and 1 electron from D will be moved, and as a result iron will have 5 unpaired electrons in D subshell. In case of cyanide, you can see at the bottom of the slide there is written Fe plus 3 and there is a dark line that is showing that be, be, uh, before this line there are two unpaired electrons and one single electrons, and after that all the paired arrows are showing that these are the six electron pairs donated by six cyanides. Cyanide is a strong field ligand, so it pushed back unpaired electron of d subshell into previous orbitals, and there is only one single electron that is present in unpaired form. That's why the hexacyanoferrate complex will show its paramagnetic moment equal to one electron. This is description of the same complex, but this description is according to CFT, the degenerate d orbital of metal ions. This line, this is showing that all the orbitals are at same energy level, but when ligand approaches to central metal atom, so in case of octahedral complexes, the ligand come along the axis. That's why the two lines at higher energy level are showing dx square, y square, and dz square orbitals. That's why the energy between axial orbitals and ligand is increased, and the non-axial orbitals are at lower energy level. This is a strong field ligand, the delta small triangle. This is showing the crystal field splitting energy. Crystal field splitting energy is the energy gap between T2G and EG orbital. When there is a strong field ligand, then this energy gap will be much higher and electrons are not capable to move from T to G orbitals to EG orbitals. So that's why in this case there is only one unpaired electron and its paramagnetic moment will be equal to one electron. This is a second case of uh, octahedral complexes. Iron again has 26 number of electrons, 6 electrons are available in d and 2 electrons are in s2 orbital. But when it goes into plus 3 oxidation state, 2 electrons from s and 1 electron from d will be moved, and after that its d orbital has 5 unpaired electrons. The ligand in this case is a weak field ligand. It is not capable to push back these orbitals and to make them paired. That's why all of the electrons are as singular. The orbitals involved in hybridization are sp3d2. Now the d orbital at the last, d4, will be involved in hybridization, and the cross, double cross, is showing that all of these 6 electron pairs are being donated by chloride ions, and molecule complex will show its paramagnetic moment equal to 5 unpaired electrons. This slide is showing magnetic behavior of the complex according to CFT, as we studied in our second last slide, that when ligand comes towards a six coordinated metal, so approach of ligand is along the axis. The energy between axial orbitals and ligand electrons forces the axial orbitals to go to a higher energy level. This is a weak field ligand. That's why we can see the energy difference between T2G and or EG orbital is less, and electrons can easily move from T2G orbitals to EG. Less crystal field splitting energy supports more paramagnetic behavior, and higher crystal field splitting energy supports less paramagnetic behavior. In this case, there are total 5 number of unpaired electrons, and both of these iron complexes are paramagnetic. But paramagnetic moment for chloro ligand is equal to 5 electrons, and for cyanide, the magnetic moment is equal to 1 electron. This is a short description of the complexes that we have discussed in the previous two slides, that hexacyanoferrate has one unpaired electron and its paramagnetic moment will be equal to 1 electron, and it is an inner orbital octahedral complex in shape. Its hybridization is dsp2. But hexafluoroferrate has 5 unpaired electron and its paramagnetic moment will be equal to 5 unpaired electron. It's an outer orbital complex, and its mode of hybridization is sp3d2. This is a summary of hybridization. I think so. You are very much familiar with the hybridization since your higher secondary school. You are uh, studying about hybridization, so I don't need to explain too much. This is first for your reference, that if you have some confusion, you can remove your confusion from this slide. Here are some questions. Encircle the most appropriate statement. Cutting and overwriting is not allowed. This is some common instruction that you are supposed to do, not in your offline exams. Actually, I took this data from my previous year data. That's why this line is written as it is. But for now, as much as I know, the exam from for your current semester will be online, and I think so. I'm not sure that whether the mode of exam will be MCQs or you have to write some theoretical answers. But anyhow, if it is in MCQs mode, then I think so there will be a very limited time for you guys to answer that question. And if it is descriptive mode, then definitely there will be some time slot for you for a given question. And I am also taking your quizzes in the form of MCQs for your practice. so that you will be easy for you if your exam is in online mode. So the first question is, well-known diamagnetic substances are calcite, quartz, water, or all of these. Quartz, you know, it is a silica. Calcite, it's a calcium salt. So you must give me the answer. As P is greater than 1, then Chi will be. P means magnetization. It's also sometimes written as P and also sometimes written as P. P is particularly magnetization of paramagnetic behavior, paramagnetic materials. So whether it's P or M, the meaning of both these two symbols is same. Greater than Chi, then negative, positive, no change, none of these. I think it's a very simple question and you must know the answer. Which of one of is not paramagnetic? So it means three of these compounds are paramagnetic, one of them is diamagnetic. Molar susceptibility is expressed. Susceptibility is usually found in molar form in grams, and further it is converted into molar. And I think so in any of the earlier lectures I have given a calculation of this molar susceptibility. In FeF6 hybridization, there are two possible options, DsP2 or DsP3 or sp3d2. One of them is present in these options. Last one is on this slide. Magnetic flux density is expressed as WTGRF. So some short answers that you have to reply me in Google Classroom. What is magnetic flux? What is gram susceptibility? The participation of electron in magnetic property is high. Why? Explain in detail the process involved in creation of magnetic field. Actually, this lecture is the closing lecture of third week. In a week, you guys are attending 3 lectures per week. So I thought after 9 lectures, I have to conduct MCQs or short answer type exam of you. That's why I have mentioned these questions not only related to this topic. I took questions from all of the previous lectures. And for magnetic flux, I think so. I have presented so many times the example of student-teacher relationship, and one of my student, Mr. Masood, is irritated with that example because he says that whenever you present this example, my mind goes to that situation and I forget that in which scenario this example is being presented in this course. Gram susceptibility and molar susceptibility, these are the two uh, magnetization units, and I am giving you a clue that susceptibility is a ratio of two magnetic field strengths. The participation of electron in magnetic property is high. This is related to paramagnetism. And the last one is explain in details the process involved in creation of magnetic field. For this one, I remember that I give you a comparison of flowing of electron or current in a wire. So you can compare the orbital model of electron with the current flowing through a wire. With this, I would like to say Allah Hafiz. Thank you so much for listening this lecture and get ready for the quiz in coming week. Assalamu alaikum. Allah Hafiz.